Welcome back. This is the third video from lecture number 2, and we are looking again at the what's called a semi-log graph, which means one axis is logarithmic, so it does that weird powers of 10 thing, and one axis is normal or linear, where each interval is the same, whereas here each interval is the same multiple or ratio. Okay, so this is a question for you to tackle, and again, I just want to make the point that as far as learning is concerned, there's always more value to trying to solve a problem than there is to seeing how somebody solves it. Seeing the solution before you have tried really hard is not very effective at teaching you anything. So don't be afraid of the math. But also I would point out that it takes a lot of practice to see these things easily and kind of naturally. So if you're struggling with this, understand that I've taught a lot of students who are kind of top tier, highly prepared nerds who also struggle with this when they start looking at it. And there's nothing wrong with that. It takes time. Okay, so I said that, and here we go with the last thing, which is what we actually do in research. In research, I don't see a lot of graphs like this in biology. I see some in engineering, but not really in biology. And we would rarely graph a growth curve or exponential growth or bacterial growth. We would rarely graph it this way. We always have to do something that makes it a straight line. So we're either going to do this kind of semi-log graph, or more commonly, we do a log transformation. Okay, so we often log transform the data. So that means we take the logarithm of the data, and then we do the statistics and graphing, and then we take any conclusions we can from it, and then we untransform the conclusions or the answers. And that's beyond what we're going to do here. I just want to show you what log transformation looks like and what it does. So let's back up and talk about logarithms. A logarithm is a math thing, and we show logarithms this way. We write log base 10 of some number equals some other number. So log base 10 of z equals q. If that's true, then what's also true is 10 to the q power equals z. So 10 to the q power equals z. That's really what this is saying. That is explicitly what this is saying, or more or less, whatever. So an example would be if I tell you that we have log 10, some unknown number of cells per milliliter. If log 10 of that unknown number equals 5, so log 10 of that unknown number equals 5, then that unknown number is 10 to the 5th power. It's 10 to this power equals this, where 10 to the q equals z. So we don't do these things in our head if they're anything other than a power of 10 with a round power. 10 to the 5th power is just 10, or it's just a 1 with 5 zeros. 10 to the 6th power is a 1 with 6 zeros. So those are big round numbers that we can pretty easily wrap our heads around if we just remember a few rules, like 10 to the 5th is 5 zeros. But anything in between is beyond what we can do in our heads and beyond what we need to do, because we have calculators. We have computers that do the logarithms for us. So I have a program on my phone that could easily take 10 to the 3.2 something power, or take the logarithm of 3.2 or whatever. We have apps for that. So we're not going to be doing this calculation, but I want you to be able to understand what the graph is. So here is the same data log transformed and graphed. So now what we have is the same x-axis as time. So this is time, just like in previous graphs. But now we have a different y-axis once again. So each data point, we've taken the logarithm of it, base 10. And so this axis is now, instead of population in cells per milliliter, it's the logarithm, log base 10 of population cells per milliliter. So this is what you would see in a research paper most often. Certainly all of my papers, this is how we graphed it, for a lot of reasons that we don't need to get into. I just want you to understand what you're looking at here. So here we see on the y-axis 3, 4, 5, 6. So let's think about that. If log 10 of the population in cells per milliliter equals 4, what is the population of cells per milliliter? So if log 10 of this equals 4, then what is that population of cells per milliliter? Well, I'll tell you, it's 10 to the 4th power. If you can go back and verify that on the previous slide where I showed you those kind of rules. And if the log of the population is 5, then the population was 10 to the 5th power. And so you can look at these graphs and say, okay, well, it's a logarithmic scale, so, or it's log transform data, and that's what it says. So I know that a 5 actually means 10 to the 5th power, and I know a 6 means 10 to the 6th power. And if we go back and look at that slide, just wait for it, we go back and forth, and we get the same same looking graph. Sorry, depending on whether we use semi-log paper or whether we log transform. So now let's just think for a second, what was the y-axis when we were looking at the semi-log paper? Was it log 10 population of cells per milliliter, or was it cells per milliliter? Think about that for a second. And let's go back. It was just the population in cells per milliliter. This is not log transform data. These are the actual data points. So this is 10 to the 5th power, and there are data points around that, 10 to the 6th power. Whereas if we log transform the data, what we're plotting is the logarithm of 10 to the 5th or 10 to the 6th. And the logarithm of 10 to the 5th is 5. The logarithm of 10 to the 6th is 6. I'm not going to make you set up these equations. I am going to expect you to be able to read this graph and tell me what it would mean if there was a dot on this 5. So that's what it is. I want you to be able to read these graphs. This point here, if we look over here, 4.5. So it's 10 to the power of 4.5 is what this actual data would be. 10 to the power of 4.5. This would be like 10 to the power of 4.2. And again, that's not something we do in our heads. We just ask a calculator, what is 10 to the power of 4.5? And we get that number. We use spreadsheets for this stuff. So, will you log transform data on the test? No, you will not. I only showed that to you because that's what you would see in research articles. It is important that you can read all of these graphs and that you know the differences between the graphs. It's important that you can understand what you're seeing, and if I say, what is this number, or ask you a question about the population, pointing at a dot, you should be able to tell me about the population at that dot. It's also important that you understand why we use these weird scales. So not necessarily why we use this one, but why would we use this one? This is common in engineering, and this one is easier to follow for a lot of people than the log transformation. So why do we do this at all? Why not graph it this way? We're graphing the same numbers. These are the same data points that we have here. We have just changed this axis. So I want you to make sure you go back and understand why we do that. And that's important. And then the last thing is you should have a clear concept in your head for what is doubling time. That is a really important thing. And if I say a short doubling time, you should know that that means something in particular. That means the bacterial population goes up really quickly. And a long doubling time means the population increases or grows very slowly. So let's end this video here so that we can move on to other topics and give them the proper attention.